Okay, so it's my pleasure to introduce you Eric. Eric Cornel, he was a student in Pasadena, California.
Cambridge, Massachusetts. Oh.
No, but after. You were in Caltech.
No, Stanford.
Stanford, sorry. He was in California, and then he moved to Massachusetts. And then we met. We were together in graduate school at MIT, and we were together in a room that Eric was trying to measure oscillation of ions to try to understand mass ratios, and I was trying to trap atoms. And we spent many nights together, and today I recall him a very interesting fact, that one day I was lying down in the floor, aligning my instrument. Suddenly I see a monster coming to me. It was a big rat. So even in places like MIT, a rat are also interested to come into the labs to learn physics. And anyway, Eric has in his life a big determination for precision, and I think it's not just a lucky that he got condensation. He has the right personality to pursue and to really go in detail and reach the things. So for many years he was doing the right thing, fixing parameters, fixing things that didn't work, and finally in '95 he will obtain, by the first time in a controlled way with trapped atoms, the Bose-Einstein condensation, which is very interesting state of matter for a type of atoms that are called bosons, which open up a whole window of possibilities for many people, including me. So many people around the world start to work in this ultra-cold matter because it has fantastic properties and new effects. And today, this is really a workbench for many, many things. We believe that almost all fields of physics are being benefited by this discovery, by this achievement of Eric. So condensed matter, field theory, statistical mechanics, thermodynamics, and many others, including atomic physics. So it is really a pleasure for us and an honor to have you here, Eric. Once more, right? You already came to São Carlos, so it's a pleasure to have you here. And I'm sure he will know what to say better than I. Dan said to me that the introduction has to be as long as... No? Well, the introduction has to be very short, so the speaker has to have all the scenario to show to us. So Eric, please go on.
Thank you very much. Thank you very much. It's a great, is this sound okay? Maybe it's a little too booming or something. Okay, a great pleasure for me to be here. I'm going to move this a little further from my mouth. How's that? Is that okay? I think maybe not so explosive. Good. I'm very happy to be here. I'm going to tell you an experiment today which has, it's not really an experiment about Bose-Einstein condensation. It's an experiment that uses Bose-Einstein condensation to measure some other physics. So as a tentative title, I tried, is warm glass stickier than cold glass? I see that most of you are young physics students, and when a young student comes into my lab, I try to teach him or her many things, and one of the things I explain to them is that one of your jobs will be to, in essence, to sell your physics research, to convince other people that your physics research is interesting, and towards this end, you have to think very carefully about the titles of both your papers and also your talks. You want the title to be interesting, not too dry, not too boring, but also not too hysterical, not too crazy. My opinion is this title is a little bit too dry, so I have a more exciting, let's see. Oh yes, this is better. The catastrophic implosion of the universe. Is it coming sooner than you think? Yeah. Okay. That's at just the right level. Not too crazy, not too hysterical, but enough so that maybe you'll pay attention. And really this has to do with, in the end, it has to do with Heisenberg's uncertainty principle. What does Heisenberg tell us? Basically, he tells us it's very, very hard to sit still. If you have a particle and the particle is sitting in a bowl, the bowl can never have exactly zero energy. It can't be exactly with no motion at the center where the potential energy is zero, because then Heisenberg says, no, this violates the uncertainty principle. You can't simultaneously know where something is and how fast it's going. No, that's against the rules. So anything, if it oscillates, it always has at least 1/2 times the Planck's constant times the frequency nu. Always at least this much energy. That's called the 0-point energy. Heisenberg says so, and he's right. And it also applies to guitar strings. If you have a guitar, and even if your guitar is at absolute zero, so there's no thermal excitations on your guitar string, each mode, the fundamental mode, all the higher harmonics, and in the guitar string, and in principle, it can oscillate up and down, perpendicular to the frets or parallel to the frets. So there's two polarizations of guitar strings. Each of these modes must have 1/2 times h times nu. 0-point energy applies to every wave as well as to every particle. And it doesn't just apply to particles, it also applies to light, to oscillating electric fields. Heisenberg says he has sort of a version of the uncertainty principle. It's not so much due to him, but it's an extension that says you can't simultaneously know how big an electric field and how fast the electric field is changing, which is of course the same as the magnetic field. So these two things are connected, and every single mode of the laser, of the optical field, I should say, should has at least the 0-point of energy. And it applies to every single wavelength or color of light and every single polarization. Okay, so for instance, here in this room, okay, unfortunately the boundary conditions are sort of complicated. So we are going to assume that the room is a rectangle and the walls are made of some nice conducting material, and we can add up all the modes. There's a mode which has a node here and then a node here, but then there's a mode with 3 nodes in this direction and 10 nodes in this direction and 20 nodes in this direction, all the polarizations. As you get to shorter and shorter wavelengths, the density of these states becomes higher and higher. There's an enormous number of modes of the electromagnetic radiation in this room. Okay, so we've talked about Heisenberg for a while. Let's think of some other famous physicist. Oh, how about Einstein? Oh, good. Okay. He says E equals mc squared. And that has implications for gravity. If we have this is supposed to be a spaceship. If a spaceship goes past some box and the spaceship's trajectory bends, we know that inside the box there's some mass. If it bends more, there must be more mass. So there could be more mass in this box, or it could be more energy, because energy, E equals mc squared, the m has gravitational implications. Maybe this box has more energy than that, and therefore the gravity inside, coming from this box is stronger than the gravity coming from this box. Okay, now let's ask ourselves a question. If we have a box which is 1 meter on a side, 1 meter wide, 1 meter long, 1 meter tall, and then we look at all the different electromagnetic modes in there, how much mass is corresponding to the energy of the 0-point fluctuations inside that? And it's a lot. 10 to the 28 kilograms. Even to keep it as small as 10 to the 28 kilograms, I had to impose a cutoff, and in principle it should be even larger than this. It's an enormous amount. So let's put these two things together. Werner Heisenberg, Albert Einstein, they come together and they come up with a conspiracy, a terrible conspiracy. You add quantum mechanics and general relativity and we get sklooch, we're all dead. Now sklooch is it's not really a term in Portuguese or English, but what it means is kaboom. Basically, if you have a box which has 10 to the 28 kilograms, there's something called the Schwarzschild radius, which is the radius of a black hole, and that is already as large as 1 meter if you have 10 to the 28 kilograms. So basically, under the gravitational self-attraction of all the 0-point energy inside of a box, even as small as 1 meter, that should implode upon itself and form a black hole. That sounds a little scary. Okay. You might think, okay, we have a box here, and that's attracting, and next to it we have another box, and that's attracting, and maybe there's some very delicate balance. You know, this box is just on the edge of imploding, but it doesn't implode because there's another box which is pulling it apart. But if you think about this, this is a very unstable equilibrium. If any one of you in this room moves so much as one finger, now the equilibrium is broken and that will collapse and then everything else will collapse into it. You may be wondering what happened to me. I used to have 2 arms. Well, boom, it's gone. Actually, that's not it, but still it's something to think about. So what is, we ask ourselves, these days maybe the most exciting area of physics is astrophysics of cosmology. And the most important result from this, if you look out into the universe, what you notice is that we're not all dead. Yeah, it's actually a very simple measurement, but it's very important. It has great implications. For some reason, we haven't all imploded. And then now you ask yourself, also theoretical cosmology is very important, and maybe at least one of the most important questions in theoretical cosmology, the understanding of the universe, is why aren't we all dead? I mean, why is it the case that the gravitational effect of the field energy is many, many million times smaller than it's supposed to be? In fact, maybe the most interesting thing is that it's not exactly 0. It's shown to be a number which is slightly different from 0, which is called the dark energy of the universe. But the natural scale of the dark energy of the universe is something like 10 to the 28 kilograms per cubic meter, and yet it actually works out to this much, much smaller number. Hard to understand. So here's a trial answer. Maybe these 0-point fluctuations I'm telling you about, maybe these aren't really real. You know, many of you are experimenters, you have friends who are theorists, and you know how theorists are. They're a little bit crazy. They come up with these convenient ideas just because they're theoretically convenient, but maybe they're not real. Maybe these are sort of imaginary fluctuations. But no, these 0-point fluctuations, these small fluctuations of the electromagnetic field are very real, and they can be measured. The field, roughly speaking, the field of physics, which is interested in seeing these fluctuations, is called quantum optics. But seeing the fluctuations is a little bit difficult, and today I'm going to explain to you an experiment we use for measuring these fluctuations. We use an atom. Okay, we use a cold atom. An atom, this is supposed to be an atom. If I apply an electric field to the atom, it's neutral, but the electric field polarizes the atom a little bit, and then that dipole interacts with the electric field, and I get an energy which is proportional to some positive, small positive constant times the local field squared. Now, if I have a mode of the electromagnetic field which is traveling along, first it looks like the solid line, a little while later it looks like the dotted line, a little while later it looks like this. If I take the average of the field of any mode that's propagating through space over time, if I take the average value of the square field, the average value is uniform across space. So if I put an atom here, it feels an energy, but the energy is the same here, it doesn't really do anything. But if I take a piece of glass, and now I have a 0-point fluctuating mode of the light that comes in, it hits the glass, some of it is reflected from the glass. And it's reflected with an opposite phase, which means that if I look at the intensity profile of this mode which comes in and comes back, there's a standing wave component which has a local minimum right at the surface of the glass. When it's reflected, there's a phase change of pi when it reflects off the glass. So now, if I take an atom and I put it very close to the glass, the atom says, oh look, locally the intensity of this 0-point fluctuations is not uniform, and so I'll feel a force. When you put an atom close to a piece of glass, or to anything really, it feels a force called the Casimir force, or the Casimir polar force, and it's pushed around when atoms are very close to surfaces. So that's the experiment we're going to do, is to measure this Casimir polar force. That was done by a family of students of mine, but the final student was John Obrecht and Rob Wild. We had very important help from theoretical physicists in Trento, Mauro Intezza, Lev Pitayevsky, who's only a virtual 0-point Italian, but he fluctuates there in Italy, and Sandro Stringari. And then, of course, this field was really founded by Fritz London and Casimir, and important work done elsewhere as well. And in terms of measurements of the Casimir force, we follow in traditions of people like Ed Hines and Alain Aspect and other people as well. We did a particular interesting measurement done at very long range, and in particular, we were studying the effects of finite temperature. Okay, some vocabulary. When you put two surfaces very close to each other, there's an attractive force, and that's called the Casimir force. If you have an atom and it's attracted to a surface, that's called a Casimir polar force. In some sense, these experiments are less easy because, are more easy. It's more easy to measure the force between an atom and a surface than between two surfaces because atoms are are very pure and very clean. You know, there's never any electric charge on an atom. Whereas if you have two surfaces, I hope none of you are condensed matter physicists who study solids, but solids are dirty, you know, impure, ungodly. You know, atoms are pure and more like God in this respect. Okay, so in some sense we're priests in atomic physics. Okay, all right. So we're going to study this force. Unfortunately, there's not just a single mode of the electromagnetic field. There are many, many different modes of long wavelength and short wavelength, and they come in perpendicular to the glass and at different angles, many different angles. And so in order to come up with the total force, it's necessary to do an integral over multiple dimensions. Now, I'm an experimenter, and when you, as you all know, or probably you haven't learned yet, but when you become an experimental physicist, you are issued a card from the union, from the syndicate of experimental physicists. And in order to get this card, you have to make various promises. One promise you have to make is, I will never do an integral in higher than one dimension. Integrals in 2 and 3 dimensions are only for the theorists. Otherwise, they'll be, the theorists will be upset, there'll be a strike. It's necessary for everyone to have a nice, secure job. But I am allowed to do an integral in only 1 dimension. So what I did is I assume that all of the intensity of the laser light comes in just at normal incidence. And now I'm just doing integral over all the different frequencies, but I weight it by this different by the different amounts of the different phase space, and I come up with I have high frequency wiggles and low frequency wiggles, and when I find if I add them all together, the wiggles go away, and I have a single smooth curve that comes down like this, and it comes to a local minimum of the glass, and the atom sits here and it feels a force. And I did this calculation. I did this integral, me, an experimenter. I did this integral by myself. I'm very proud of this. And I got an answer which was within a factor of 3 of the correct, actual understood. I was very, very proud, but there's a problem. The problem is that alpha there, that's a positive number, which means the force is the potential is a negative potential. And an atom, according to my calculation then, it should be attracted away from the surface. I should say is repelled from the surface. Experimentally, we know if you put an atom close to a surface, it's attracted to the surface. So my calculation may have been pretty good, only a factor of 3 off, but somehow I made a minus sign error. Okay, well maybe this is good. Maybe this minus sign error is going to save our lives. Maybe this discrepancy between my baby theory and the actual experiment is the way that prevents us from all dying. It turns out, no, that's not the reason. The real reason is that I neglected other sorts of ways, in particular internal fluctuations. If this is a piece of glass, then there are fluctuations of the electromagnetic field within the glass, and some of them come up at a small angle and undergo total internal reflection, and a little bit of the electric field extends beyond the glass, and that electric field has a local field maximum at the surface. The light which is coming in at normal incidence and bounce off has a local and field in a minimum here. This has a maximum. And it turns out that if you add up all the different modes, yes, the force in general should be attractive. Okay. And interestingly, there was some theory from the Italian guys, and we'll come back to this, that says if you look at the finite temperature effects, it's possible to even make this force in principle repulsive. But we'll revisit this idea later on. So if we include not just the quantum fluctuations, but also the thermal fluctuations, this is the, in logarithmic scale, the potential between the surface. This is the distance between the atom and the surface at short range. This is usually called a van der Waals force. Once you go to a distance which is comparable to or longer than the wavelength of the fundamental excitation of the atom, it falls off as 1 over z to the 4th. If you have instead black body radiation, by the time you get out to a wavelength which is comparable to the peak of the black body spectrum, it falls off only as 1 over z cubed. And the Trento guys show that if you're out of thermal equilibrium, if the temperature of the substrate is different from the temperature of the ambient gas, there can be a particularly long-range tail that falls off only as 1 over z squared. We'll come back to this force in a little bit. The range where we do our experiments is sort of close to where these 3 different ranges undergo crossovers. So we measure the potential as a function of the distance, but in no place is it really cleanly 1 over z to the 4th, 1 over z cubed, 1 over z squared. We actually have to measure the number and compare it to an exact theory. And the actual coefficient out in front matters. But we have these wonderful theorists who can do these calculations for us. Okay, so we do an experiment with a Bose-Einstein condensate. We start with atoms at close to room temperature. We cool them down first to 400 nanokelvin. This gas here is essentially a regular, something like a Maxwell-Boltzmann distribution of atoms. We get it colder, a Bose-Einstein condensate occurs. We get it colder yet at 50 nanokelvin. We get a very cold, very compact gas of atoms. It's interesting. In this experiment, we are trying to study the effects of finite temperature effects on the Casimir-Poldr force. But when I talk about it, I'm not talking about the temperature of the condensate. I'm talking about the temperature of the substrate and the ambient thing. For all purposes, this gas is at temperature 0. And really, we don't take advantage of the fact that it's a Bose-Einstein condensation. The only thing is that if you want to make a precise measurement, you'd like to keep the atom close to the surface for a long time. So you have a lot of time to make a very precise measurement. Keeping atom close to the surface for a long time means the atom should be moving very slowly, very cold. Plus, we'd like to have very good signal to noise, which means we want to have lots of atoms close to the surface. So we want high density. It turns out that if you want high density atoms, very cold atoms, you put it together and you want high phase space density, which means Bose-Einstein condensation. So it's not particular to the condensate. It's just a useful source of atoms for us. So here's our experiment. It's very complicated. There's a vacuum chamber. I'm going to zoom in on the place where the condensate is made and where the surfaces live. If I look inside a little window there, I see I have a glass chamber under very, very high vacuum. Inside there, I have a rack made out of glass, and on the rack, I can put various different substrates of different materials: silicon, glass, quartz, titanium. We measure various different surfaces. We put it inside there. We bring in the atoms in here. We suspend them with a magnetic trap right here. We cool them down, and then we move them up and let them almost touch the surface, and we measure the force. One of the things that I learned when I was a graduate student, I took a course in atomic physics from Dan Kleppner, and what he told me is that if you want to measure something very precisely, you should convert the thing you want to measure into a frequency. Experimenters are good at measuring frequencies, they're bad at measuring almost everything else. So we have the atoms in a magnetic trap, they oscillate back and forth. We take the magnetic trap and we move it very gradually close to the surface. Now this is the magnetic force. In addition to the magnetic force, we have the force which is emanating from the surface. It moves the atoms over, but it also, because there's a first derivative of the force, a second derivative of the potential, it changes that frequency a little bit. So if we measure the resonant frequency of the atoms moving in the trap, that resonant frequency changes when we bring it close to the surface. And we can measure frequencies very precisely, and this way we can make a very precise measurement. In spirit, this experiment is very much like an atomic force microscope, where there's basically a thin point on the end of a little vibrating spring, and you measure the frequency, and when you get close to the surface, they measure a change in the frequency. This is how most atomic force microscopes work. We're doing atomic force microscopy with individual atoms. And in contrast to a traditional atomic force microscope, which is done at a range of a few nanometers or less, we're operating at many microns, thousands of times larger differences, where we're able to see these very small differences which come from the finite temperature effects. So here's the actual experiment. We create a Bose-Einstein condensation. We move it close to the surface. We cause it to oscillate. We take a little picture, we freeze it, and we measure where it is. And then, and then we take a series of measurements, and we see that it's moving closer and further. We fit this to a sine wave, and we extract a frequency. And you can see this is between 0 and 4 milliseconds here. We take a little break. We come back 1 second later, and it's oscillating almost with the same. There's been very little decoherence, very little dephasing or damping over the course of 1 second. So we can count hundreds of oscillations, fit the phase very precisely, and extract this frequency to perhaps a millihertz if we work hard. So we can make these very precise measurements and see changes in the frequency at just a few parts per million. Here is data taken at room temperature, and the blue line is a theoretical prediction. Here's the distance between the atoms and the surface. Here is, actually this is not the force, but the force has been converted into units which are shift in the frequency. It's a very small force. And if you look carefully, you might believe that the atoms agree more precisely with the blue line than with the black line. The blue line is a prediction for 300 Kelvin, the black line is a prediction for 0 Kelvin. But if you want to believe that the data is agreeing more with the blue line than the black line, again, you have to be very pure of heart. If you have any doubt or sin in your brain, then you can't see this effect. I have to admit that when I looked at the data, I was not able to see the effect. So we thought, okay, we're interested in seeing how the effects of finite temperature can change Casimir-Poldr forces, basically modify vacuum fluctuations, add thermal fluctuations, see this different performance. How can we see this? And the guys from Trento were very helpful. They said, if you make it non-equilibrium, if you make the glass surface around the outside of your chamber at room temperature, and you make the substrate very hot, you will see a very, very large enhancement of the finite temperature effects. The way we do this is we take a little black paint, and we paint the back surface of each of these, we paint it black, and we shine in a laser which passes through the glass surface without absorption, heats up these chips, and the chips are supported on these glass racks, which are very good insulators. We have interferometric ways of measuring the temperature. We can pass a laser light through the glass and bounce it back off. We can see the fringes, and we can very precisely measure the thermal expansion and determine that the rack itself does not get very hot, but we can, the wafers instead get very hot. The outside glass stays at room temperature. So what happens is, if we make the glass hot, we are enhancing the thermal fluctuations within the glass. The attractive part, the evanescent waves here have an attractive force. The light which is coming in from the outside, that bounces off, has a local minimum there. That generates a repulsive force. It turns out at 300 Kelvin, if everything is in thermal equilibrium, there's an accidental cancellation. The forces coming in, the force coming from light coming in and the force coming from light going out almost exactly cancel, and you have the finite temperature effects are very, very small. But if you break the thermal degeneracy, if you make this hotter and this colder or vice versa, you can get much larger thermal effects. And here's our data. In every case, the outside temperature is about room temperature, about 300 Kelvin. There's basically our old data again. In equilibrium, we come out of equilibrium, we make the surface of the substrate 400 Kelvin or 600 Kelvin. We see very strong differences. If I average that data together, you can see, for instance, that if you're a distance of 8 microns or say 6 microns here, the additional force associated with the thermal effects can be a factor of 3, out here even a factor of 4 times larger. So the thermal corrections can become very, very large. Typically, people tried to see thermal corrections to Casimir forces. They were doing this at just a few nanometers, and the corrections would be a part in 1,000 or something, and it was very difficult to do those experiments. So I should tell you, it's actually very difficult to do this experiment too. I've removed all the things that make it sound hard, but in fact it took us a long time. Here now is just sort of averaging over distances. We just see the effect of increasing the temperature of the substrate. If we go back to this picture here, you can see if we actually made the glass, right, what we typically do is we make the glass hot and the outside envelope cold. If instead we make the glass cold and the outside envelope hot, you can enhance the repulsive force and suppress the attractive force. And in principle, the theory tells you you ought to be able to change the sign of the Casimir force. Make the Casimir force repulsive. That would be very exciting. You have a piece of glass, you put the atoms close, and the atoms float on a magical repulsive potential and just slide along as if they were skaters on a piece of ice or something like that. It turns out experimentally that's very difficult, because if you go into a vacuum chamber and you make your vacuum chamber hot and you make one little thing inside your vacuum chamber cold, that cold thing effectively becomes a magnet for dirt. All of the dirt in your chamber sticks onto the glass. And instead of measuring the Casimir-Poldr force, you measure, basically you have a lot of dirt on your glass, including charged particles, and eventually you just sort of measure electrostatic potentials and so on. It's less interesting. Anyway, we do see this very strong effect. And we understand it from understanding that the fluctuations come from 2 different families of fluctuations, external light and internal light. Okay, so let's review with some questions. Why hasn't the gravity from the energy of the 0-point fluctuations imploded the universe? That's question 1. Question number 2, even more important. Let's see if we have, and caused us all to die. Question 3, horrible, painful deaths. Now here I will admit, I'm making a small exaggeration. I actually think it would not be so painful, too fast. You know, probably not so bad. So in order to attract your attention, I'm exaggerating a little bit. Okay, what are the answers? I actually don't know. But what we can say is that hopefully we understand the Casimir-Polar force between an atom and a dielectric surface. We understand why it is usually attractive and not repulsive, and why, therefore, warm glass is stickier than cold glass. With that, I think I'm going to stop here. Thank you for your attention, and ask if you have any questions.
You've been thinking about the physical effects of all this energy floating around in the vacuum. Now, we have serious energy problems on Earth.
Yes.
Have you thought of any good way to make use of all this energy that we're surrounded with?
I have not thought of that. There are many people who will tell you that it's possible to build a machine which can extract energy from the zero-point energy. In fact, in the United States, there are people who hold patents on this idea and have attracted investment dollars to come in and build the machine. My personal opinion is that the main point is the investment dollars and not the energy, but okay. So far, there's not been strong results there. There's something about this energy which is somehow intrinsic to the vacuum, hard to suck it out of the vacuum.
Could I interest you in investing in the corporation I conceived of many years ago, the Zero Point Corporation?
Absolutely. I think I would make piles of money, wealthy beyond my wildest dreams. We'll talk.
We'll talk.
I'm going to, while you're thinking of another question, I'm going to show you, I had a somewhat short notice, and I'm missing a slide, and I'm going to describe to you the slide which I forgot to bring. Or, forgot is one explanation. Well, if we go back to this original 300 Kelvin data here, where we took a lot of data, this blue line is a calculation based just on the Casimir-Polar force and quantum mechanical fluctuations. You have to know about the index of refraction of the glass and of the frequency dependence of the index of refraction of the glass and of the frequency dependence of the polarizability of the atom. A lot of things go into the calculation, but I think these are very serious guys. And when they're all done, they make the calculation. We actually plotted, and I don't have this plot, the residuals, the difference between a calculation and a measurement, and they're very small. And then we decided to interpret this another way. There's at least a hypothetical idea that gravity, the force of gravity between two objects, which is very well known if you look at the Earth and the Moon, and it's measured in the laboratory at the distance of perhaps 1 meter or even as small as 1 centimeter, there's no empirical reason not to imagine that the force of gravity at the distance of a few microns could be perhaps very different. And so we interpreted the same data as a limit on the possible deviations from the force of gravity at short distance, which was competitive with the other measurements. And I wouldn't say it's better than, but not especially worse than the other measurements at 5 microns. So we were able to do something like particle physics. The idea is that there's some particles with a possible Yukawa range as much as 5 microns, and in this case you'd see a very large, you'd see a deviation from the force. Okay, it was not a particularly compelling measurement, but at least it was another application of Bose-Einstein condensation, an attempt to do particle physics. Are there any other questions? Yes?
I was wondering about the evanescent modes being repulsive and the vacuum modes being attractive. Whether it would be possible or not to maybe change the density of those modes by shaping the surface in such a way that you could get a higher, in some localized space, a higher density of the repulsive modes, which would give you a net potential, maybe minimum, or some place where you might be able to trap the atom.
Yeah, I think that's a great idea. And we tried to shop around to some theorists, these ideas about maybe, let's see if we can find a good picture here. Yeah, what if we could put maybe multiple dielectric layers on here, or things we could give transverse structure in this direction?
Yeah, something,
things
instead of just having a flat surface.
Yeah, we thought about that, and we shopped around to a few of our favorite theorists saying, wouldn't you like to think about this? And they said, well, it's calculationally very intensive. Why don't you tell us what your intuition tells you should be a very likely pattern, and we'll do a calculation for that. And I said, I have no intuition. Couldn't you just go try everything? And they said, no, we don't want to do that. So,
Well, yeah, I think the basic problem is that it's an integration over more than one dimension. So,
oh, yeah, I noticed that.
so that's why you don't have any intuition.
Yes,
but that doesn't excuse them from not doing the calculation.
I would say not. No, I thought this shows some lack of enterprise on their part. And so in the end, of course, you might say, well, as an experimenter, why don't I just go and make many different patterns and put them in there? But as I tried to explain, these are actually really hard experiments. The big problem is if you get any dirt on there at all, the dirt, as a principle of physics, dirt is attractive. And we found a lot of interesting attractive forces associated with straight charges stuck on dirt. And dirt can even include rubidium atoms, because if you let even one rubidium atom hit the surface, the rubidium atom is very happy to give up one of its electrons, and the electron goes into the surface and it becomes a little electric dipole, and that force reaches out. We spent some years trying to first make the surface clean enough and then do a series of auxiliary measurements convincing everyone else that it was clean enough to see only this very small force, which is falling off as the Casimir-Poldar forces are falling off as high powers. They are falling off as stronger powers than the electric field. So when we first measured this force, it was 200 times larger than we thought it should be. So it tells you sort of the natural scale of the systematic errors is a factor of 200 larger than the physics. We think we've really suppressed it by more than a factor of 1,000, and we feel good about it. We wrote a whole paper measuring electric fields and so on, but not completely easy. But yeah, the theorists are lazy, and in the end we decided not to do that. But I feel in my gut that there ought to be a pattern where the atoms would just sit there.
Eric, you use a thermal field, so a thermal occupation of your modes.
Yes.
It has the advantage that you're measuring thermal equilibrium, which is often a great advantage, but it also has the disadvantage that you're measuring a thermal effect. Could you excite one of the vibrational modes, for instance, with ultrasound or something, and then boost up the effect and with a precise mode?
Well,
would it be possible to organize that?
You're now reminding me that some years in the past, I gave this talk, and Dan Kleppner was in the audience. And he asked a similar question. He said, well, you could just take a laser and bounce it off the surface, and then you would get nodes and antinodes, and you could trap the atoms in that pattern there. And I said, well, yes, but that's trivial. Everyone does this now in atomic physics. That doesn't count because it's artificial. But it was hard for me to try and justify why the natural effects of temperature were somehow perhaps more interesting than constructing artificially a local maximum or minimum of the power, which people with optical lattices do every day. And I had to do that, I had to sort of invoke a class of physicists that Dan is not a part of, which is solid-state physicists. If you talk to a solid-state physicist, okay, I'll declare my allegiance. I'm an atomic physicist, and my personal opinion is that temperature is basically dirt. The only real physics happens at 0 temperature, and temperature is sort of a dirt effect on top of that. But if you're a solid-state physicist, you actually think of temperature as being an important physical control parameter that changes the whole physics, and it's very interesting. And they have this thing called phase transitions. I don't know exactly what this is about, but they think it's important. And so they like temperature. And so if you actually sort of see the forces changing with temperature, there you're doing real physics. Otherwise, you're just a solid-state physicist will tell you if you're actually operating at 0 temperature, you're just operating on a blank canvas, and you haven't actually painted the picture on it yet. The 0 temperature thing is just the framework, the steel structure of what could be an interesting material.
So you're saying that you can learn nothing about the Casimir force by doing this vibrational mode?
Nothing about?
About the Casimir force by inducing this.
I don't say that. I would say that, okay, so I'm a guy who for a living takes atoms and cools them down to 5 nanokelvin, which is 9 orders of magnitude lower than the lowest possible natural temperature. So perhaps it seems a little crazy for me to say, oh no, that shining, that's too artificial a situation to do that. We only study natural things in this experiment. But that's what I want to say, is that no, shining the laser, that's unnatural. That's artificial. We only study the natural effects of the glass itself.
Eric, I have a question. It's embarrassing, but I never could get an answer to that question, and we worked on it, and maybe you can add something. Is the Casimir-Polder effect between an atom and a wall at 0 temperature really a quantum electrodynamics effect? And I explain myself. You can fully calculate the force between an atom and a wall by taking the quantum fluctuation of the atomic dipole and then forgetting about any quantization of the electromagnetic field and just looking at the traditional electrostatic, or you can introduce delays and things like that, the force between the electric dipole of the atom and its image in the dielectric, and you get the right results as far as I know. So, and I teach my students that when it is enough to use a semi-classical of matter-light interaction, that is to say a model in which you don't have to quantize the light, it's better to use it. You wouldn't use Schrödinger equation to calculate the motion of planets, so if the semi-classical model where you don't quantize light is enough, use it. And we know there are situations where we need quantum light, but my question is, what is your gut feeling? Is this experiment of looking at the force between an atom and a wall really a quantum electrodynamics experiment?
So you ask about my gut, and I'll give you a gut answer. And that gut answer is yes, it is.
Why? So,
okay.
So now you have to argue.
Now I'm going to, the way I'm going to do that is exactly by turning your argument on its head. It turns out, in this particular situation, it is much, much simpler to quantize the electromagnetic field than to understand the quantum behavior of this dielectric material. So you tell me that, why, maybe you say, well, in other situations, it is indeed easier to think about the quantum structure of the atoms and not of the light, and therefore, why bother invoking the quantum structure of the light? I tell you, why bother invoking the quantum structure of the atoms? I mean, that's all I can say. But are there these spooky higher order correlations that are the very undefinable, irreducible hallmark of quantum optics? No, there's not that.
Okay, so your main argument is an argument of simplicity of the description.
Yes.
Okay, thank you.
The boundary condition that the dielectric introduced in the electromagnetic field are different for each frequency of the normal modes. For instance, if you
Yes,
take a very high frequency,
that's correct.
the dielectric doesn't respond.
Yes, that's correct.
So there is a band of frequencies that
Yes.
are affected by the boundary condition.
Yes.
How you take that into account?
We do take it into account. Basically, we use materials which are very well characterized materials. We know both the real and the imaginary part of the dielectric function as a function of frequency. For the atom, we also know the atom is a very, very well understood object. We understand there's a real absorption at some very high frequency. At these lower frequencies, there's essentially a polarization. And we take an integral over all this. As I say, I don't do this kind of thing because it's not simple. However, you can do a simpler version of the experiment where you assume at low frequency, you're in a low frequency limit where there is simply a dielectric constant. The same thing that you would measure if you just, basically the low frequency limit of the dielectric constant. And if you assume that the atom, again, has a low frequency limit of that. Mm-hmm. And then if you assume that's constant and don't do the integral, at a distance of 8 microns, it doesn't change the answer essentially at all. The reason being that the higher frequency modes of the light have a wavelength of perhaps, for instance, in quartz or something like that, the shifts begin in the ultraviolet. For rubidium atoms, the shifts don't begin until 700 nanometers, something like that. We're 8 times further away than that. And those forces, the differences between the naive picture of essentially DC electric field effects and the more, they only turn on at distances less than 1 micron. So the corrections are very small.
Yeah, by curiosity, why don't you do the experiment with a metal sheet?
Oh, yeah, actually, we should. And absolutely, it seemed to us like a metal sheet would be better. Because, you know, as a graduate student, I took these electromagnetic classes, and in graduate electromagnetics and in undergraduate electromagnetics, metals are particularly simple. You know, there's no electric fields, there's no transverse electric fields, you can have a surface charge in principle, but it's not like, a real metal is not like that at all. And
Yeah, sure.
Amazingly, what we found is that the metals are, in general, are much dirtier than the glasses. We can make the glass much cleaner than the metals, the reason being that the metals have a much stronger attraction for alkali atoms. Once they get on there, it's really hard to get them off. And
Yes, because the van der Waals forces will be more intense
yeah,
than
but not just the van der Waals
forces.
forces, also these sort of, call it an ionic bond, in the sense that the rubidium sits there and the work function of the steel is much higher than the work function of the rubidium. And so you get a very strongly charged particle stuck to the surface every time a rubidium atom hits. And although it seemed to us that we worked in titanium and gold and that this would surely be a better material, we never were able to get them clean enough to do these experiments. So we had to use quartz and silicon and these things instead.
Thank you.
Thank you. Thank you very much. Obrigado.